Now, this video is for those of you who may have a test on SN1, SN2, E1, E2 reactions, and you want to just learn everything that you need to know in one video. Now, I do recommend watching another video that I have on YouTube, which is entitled SN1, SN2, E1, E2 reaction mechanisms. It'll give you a good overview of what you need to know to answer these problems. So let's go ahead and begin. Which of the following compounds will undergo a SN2 reaction most readily? What you need to know is that methyl alkyl halides, they react much more readily in an SN2 reaction than primary alkyl halides. And tertiary alkyl halides, they don't work very well in an SN2 reaction. So let's identify what type of substrate that we have for each of these compounds listed below. So the first one, this is tert butyl bromide. To draw it, we have a carbon with 3 methyl groups. Now the carbon that is attached to the bromine atom, that carbon is tertiary. It's tertiary because it's attached to 3 other carbon atoms. And this is not going to work well for an SN2 reaction. If a nucleophile were to try to approach this electrophilic carbon, it's going to have difficulty doing so because these methyl groups, they block approach to that carbon, making it almost or nearly inaccessible. So it's hard for a nucleophile to approach that carbon because of those 3 bulky methyl groups. Therefore, tertiary substrates are not very good for an SN2 reaction. So that's not going to work. We can eliminate A. Looking at B, we have a carbon that is this carbon here. That carbon is attached to 2 methyl groups, as you can see, CH3 times 2. And this is a CH carbon, so it has a hydrogen on it. So looking at this one, this is a secondary carbon. So we have a secondary alkyl halide. Now just by looking at this, we can see that this is primary. The carbon that is attached to the bromine, it's attached to one other carbon atom. If you wish to draw it, you can show it this way. So that carbon has 2 hydrogen atoms. It's a CH2 carbon. It also has a bromine atom. And on the left, it has an ethyl group, CH3, CH2. So that's a primary alkyl halide. Primary alkyl halides work better than secondary alkyl halides, so we could eliminate answer choice B. So now we're down between C and D. Both C and D are primary alkyl halides. The only difference here is the leaving group. So which one is a better leaving group, bromine or chlorine? Now if you were to go to the periodic table, leaving group stability increases as you go down the group. Iodide is bigger than bromide. So iodide, because it's bigger, it can better stabilize a negative charge than bromide can. And bromide, being bigger than chloride, can also better stabilize a negative charge than chloride can. So what we need to know is that bromine is a better leaving group than chlorine. So therefore, answer choice C is the correct answer. Out of the substrates listed, this one will undergo an SN2 reaction most readily. Number 2, which of the following compounds will undergo solvolysis most readily? Now, solvolysis, this is typically associated with an SN1 reaction. It's where the solvent acts as a nucleophile. So when you see the word solvolysis, associate it with an SN1 reaction. So what we're really asking is, which of these substrates or which of these compounds shown below works best for an SN1 reaction? Now we know methyl and primary substrates work well for an SN2 reaction. The reverse is true for an SN1 reaction. An SN1 reaction prefers a tertiary alkyl halide rather than a primary alkyl halide. And the reason for this is because tertiary carbocations are more stable. For an SN1 reaction to work, the leaving group has to leave first. primary and methyl carbocations are not very stable compared to tertiary carbocations, so that's why they don't work well in an SN1 reaction. So for these types of problems, you need to look at which substrate is tertiary, and also potentially look for which carbocations can be stabilized by resonance, because that will be even better for an SN1 reaction. Now looking at answer choice A, we know that this is a primary alkyl halide. For answer choice B, if we were to draw it, we would have 1, 2, 3, 4 carbons in a straight chain. But on carbon 2, we have a chlorine atom extending from it. So this is a secondary alkyl halide. Now, we've seen this one before. That's tert-butylbromide, which looks like this. And so that is a tertiary alkyl halide. But what about C? When you see C6H5, that's a benzene ring. Now, attached to the benzene ring, we have a carbon, and that carbon is attached to 2 methyl groups. Now, attached to that carbon, we also have a bromine atom. So this carbon here, it's also tertiary, but we'll call it a benzylic tertiary alkyl halide because it's 1 carbon away from the benzene ring. So which one is better? Answer choice C or D? In an SN1 reaction, when the leaving group leaves, we'll be left with a tertiary carbocation if we started from answer choice D. Now for answer choice C rather, when the leaving group leaves, notice that this carbocation is stabilized by resonance. This plus charge can move around within the ring. So let's draw one resonance structure. We could take this double bond, move the 2 electrons here, and then we can get this resonance form. And now the plus charge will jump 2 carbons away. It will jump 2 carbons towards the double bond that moved toward it. Now we can also draw 2 other resonance structures if we wanted to. We can move the plus charge here, or we can move it there. And so this particular carbocation, its positive charge can be shared among 4 different carbon atoms, which makes it more stable rather than having 1 carbon atom to bear that positive charge alone. Therefore, answer choice C is the correct answer. This compound will undergo a solvolysis reaction most readily because it forms the most stable carbocation intermediate. Number 3. What is the major substitution product of the following reaction? So we have 2-bromobutane reacting with ethanol. 2-bromobutane is a secondary alkyl halide. The carbon that bears the bromine atom, that carbon is attached to 2 other carbon atoms. And we're reacting it with ethanol, which is a Protic solvent, due to this hydroxyl group. Now, what type of reaction mechanism will occur here? SN1, SN2, E1, or E2? What would you say? Now, whenever you have a secondary alkyl halide, the SN2 reaction competes with the SN1 and the E1 reaction. You'll get an SN2 reaction if you react a secondary alkyl halide with a good nucleophile in the presence of a polar aprotic solvent. Here we have a protic solvent, not an aprotic solvent. So for a protic solvent, this favors the SN1 E1 reaction, which usually occurs together. To get an E2 reaction, you need to react an alkyl halide with a strong base, like sodium hydroxide, sodium ethoxide, or potassium tert-butoxide. But we don't have a strong base, so we're not going to get an E2 reaction. And looking at the question, we want to find the major substitution product. So we don't want the elimination product. E1 and E2 reactions, they produce alkenes. They form double bonds. So we're not going to get an alkene as our product. Now let's talk about the mechanism for this reaction. So we know we have an SN1 reaction. The leaving group is going to leave. So this will give us a secondary carbocation. The nucleophile, which is the solvent, that makes this a solvolysis reaction. The solvent, where it behaves as a nucleophile, it's going to attack the carbocation. It could attack it from one side, or it can attack it from the other side, which gives us a racemic mixture of stereoisomers. So let's say it attacks it from the front. We would get an intermediate that looks like this. Now, in the next step, another ethanol molecule, ET is for ethyl, which is the same as this molecule, it's going to act as a base. Make sure you understand the difference between a nucleophile and a base. In this step here, the second step, where ethanol attacks the carbocation, in that process, ethanol is acting as a nucleophile. The word nucleophile means nucleus loving. Phile means love. So ethanol, when it acts as a nucleophile, it's basically going for the nucleus of that carbon. And if you think about it, inside the nucleus of an atom is where you'll find positive charges like protons. So that oxygen with the partial negative charge, it's seeking the nucleus of that carbon. And so it's nucleus loving, which is acting as a nucleophile. Now a base, bases abstract protons. Think of acid-base reactions. Here, ethanol is going to act as a base because it's going to abstract a proton. Acids, they donate protons. Bases, they accept protons. So ethanol accepting that proton makes it a Bronsted-Lowry base. When it abstracts that proton, the bond between hydrogen and carbon, that bond is going to break. Those electrons will return to this oxygen. And so we'll get this product. Now keep in mind, ethanol can approach the carbocation from the front or from the back. So we're going to get a racemic mixture of isomers. So this will be one product that we're going to get, and here is the other product. So this is butane with an ethoxy group attached to it. So we have 2-ethoxybutane. We don't have an alcohol, we have an ether as a product. And since we have a racemic mixture of two isomers, R and S, the answer is going to be D. Number 4. Which of the following is the strongest nucleophile when dissolved in a polar protic solvent? Is it A, B, C, or D? Now, the trend is different if the nucleophile is in a polar protic solvent compared to if it's in a polar aprotic solvent. Now let's talk about that. In a polar protic solvent, the trend basically follows the periodic table, where you have fluoride listed on top, and then you have iodide listed on the bottom. In a polar protic solvent, the strength of the nucleophile increases towards iodide. In a polar aprotic solvent, the strength of the nucleophile increases towards fluoride. So in a polar aprotic solvent, fluoride is the strongest nucleophile, but in a polar protic solvent, iodide is the strongest nucleophile, which is what we have here. So the correct answer is answer choice D. Now let's talk about why. Let's say if we were to place fluoride in a polar protic solvent like water. Water will solvate the fluoride ion. The hydrogen atoms of water, which bear a partial positive charge, they will be attracted to the negative charge of the fluoride ion, and they will stabilize it. Also, if you put fluoride in water, fluoride is strong enough to abstract a proton from water in an acid-base reaction, creating HF and hydroxide. And HF is not a good nucleophile compared to fluoride. So because fluoride is a stronger base than iodide, it's not very good as a nucleophile in a polar protic solvent. It can easily abstract a proton from a protic solvent like water or methanol or even ethanol. Iodide doesn't have that affinity for a proton, and so it's not going to abstract a proton from water. Therefore, it's free to react as a nucleophile. Now, fluoride will work very well in the presence of a polar aprotic solvent. So for instance, let's say if we were to use a crown ether. So this is a 15-5 crown ether. There's 15 atoms in total. 5 of them are oxygen atoms. So if we were to react sodium fluoride with methyl bromide, for instance, the negatively charged oxygen atoms, they will be attracted to the positively charged sodium ion. In fact, the sodium ion is going to sit inside this cavity, allowing the fluoride ion to be free to react with the substrate. So this polar aprotic solvent, it solvates the sodium cation. So this fluoride is not held by the sodium cation. It's free to react, making it even more reactive in this polar aprotic solvent. So what we need to know is that fluoride works better in a polar aprotic solvent, but iodide works better in a polar protic solvent. So this would be a protic solvent. Typically, you'll have an OH or an NH group in that molecule, and this is an aprotic solvent. We don't have any OH or NH groups. So D is the correct answer. Number 5. Which of the following rate law expressions apply to an E1 reaction? Is it going to be A, B, C, or D? Let's talk about B. What is the overall order of this reaction for answer choice B? Notice that it's first order for the substrate, first order for the nucleophile. So it's second order overall. Now, is this an SN1, an SN2 reaction or an E2 reaction? Because in SN2 reaction, it's a second order nucleophilic substitution reaction. An E2 reaction is a second order elimination reaction. Now this is going to be an SN2 reaction. It's a second order nucleophilic substitution reaction. SN1 and SN2 reactions, they use nucleophiles. E1 and E2 reactions uses bases. So this can't be an E2 reaction because of the nucleophile. Now, looking at answer choice C, this reaction is second order overall. It's first order in the substrate, first order with respect to the base, 1 plus 1 is 2. So it's second order overall. And the concentration depends on the base. So this is an E2 reaction. Now, SN1 reactions and E1 reactions, those are first order reactions. Answer choice A and D are first order reactions. Now for answer choice A, this corresponds to an SN1 reaction, and at the same time it corresponds to an E1 reaction. For these two reactions, the concentration, or rather, the rate of the reaction, does not depend on the concentration of the nucleophile or the base. For both of these reaction mechanisms, the rate of the reaction depends only on the concentration of the substrate and not the base. So answer choice A corresponds to the mechanism of an SN1 and an E1 reaction. So since we're looking for the rate law expression that applies to an E1 reaction, answer choice A is the correct answer. Number 6. What is the major product of the reaction between R2-bromobutane and potassium iodide in acetone? Well, first, let's draw a picture. We need to draw R2 bromobutane. So here's butane, and let's put a bromine in the front, which means hydrogen will be in the back. So bromine will be group number 1, the ethyl group will be group number 2, methyl will be number 3. If we count it from 1, 2 to 3, we're going in the clockwise direction, which is R. So that's R2 bromobutane. And we're going to react it with potassium iodide in acetone. Acetone is basically a 3-carbon ketone. It's a polar aprotic solvent. As you can see, it doesn't have any OH or NH groups. So now that we have a secondary alkyl halide, we have a strong nucleophile, iodide, and a polar aprotic solvent, what reaction mechanism will be the dominant mechanism in this reaction? Polar aprotic solvents, they favor SN2 reactions over SN1 reactions. And iodide is not a strong base, so it's not going to favor an E2 reaction. Iodide is a strong nucleophile, which favors an SN2 reaction. So we have two things that favor an SN2 reaction in this example problem. We have a strong nucleophile and a polar aprotic solvent. So now that we know we have an SN2 reaction, let's see what's going to happen. Iodide, being a nucleophile, it's going to attack the carbon that has the bromine atom. The leaving group is going to leave. And so we're going to replace bromine with iodine. Now, because iodide attacked from the back, we're going to have inversion of configuration. So initially we had the R isomer, but now we have the S isomer. If iodide is in the back, we know that hydrogen has to be in the front. So if we count it, this will be group number 1, 2, 3. It appears to be going in a clockwise direction, which is R, but because H is in the front, we need to reverse it, giving us the S isomer. So the product of this reaction is S2-iodobutane. So make sure you understand this. SN2 reactions, they give you the inverted product. SN1 reactions typically give you a racemic mixture of 2 isomers. Now, it's not a 50-50 racemic mixture, but it's more like 60-40, 30-70. It's an unequal racemic mixture of A and B. But for SN2 reactions, you get only 1 stereoisomer as opposed to 2. Number 7. Which of the following statements is not true regarding SN2 reactions? So let's go through the list. Answer choice A, SN2 reactions proceed with inversion of stereochemistry. Is that true or false? This is a true statement, especially based on last example. SN2 reactions do proceed with inversion of stereochemistry. In the last example, we started with an alkyl halide that had the R configuration. When we reacted with sodium iodide in acetone, it inverted and gave us the S configuration. So the configuration of the chiral center changed from R to S. So you're always going to have inversion of stereochemistry for SN2 reactions, as long as the carbon that has the leaving group, as long as it's chiral. Answer choice B. The SN2 reaction is a concerted reaction mechanism. This is also true. In the last example, where we had 2-bromobutane and we have iodide, as iodide approach the carbon, the bond between carbon and iodide begins to form. At that same time, the bond between carbon and bromine breaks apart. A concerted reaction mechanism is a reaction mechanism where all bond breaking and bond forming processes, they occur simultaneously at the same time, which is what happens in an SN2 reaction. So the bond that forms between carbon and iodine and the bond between carbon and bromine. So as this bond forms, this one breaks. And this happens at the same time, so that makes it a concerted reaction mechanism. Now what about answer choice C? The SN2 reaction contains a carbocation intermediate. This is not true. In this SN2 reaction, there were no carbocation intermediates that were formed. So C is the correct answer because that statement is false. Carbocation intermediates, they're a property of SN1 and E1 reactions. These mechanisms form carbocation intermediates. As a result, they are subjective to rearrangements. Now for answer choice D, this is a true statement. Rearrangements do not occur during an SN2 reaction because SN2 reactions, they don't form carbocation intermediates. On the other hand, SN1 and E1 reactions, they do generate carbocation intermediates, which means that they can rearrange. Number 8. Which of the following is a polar protic solvent? Well, let's go through each one. DMSO, this is dimethyl sulfoxide. What we have here is a sulfur double bonded to an oxygen with 2 methyl groups. This is a polar aprotic solvent. There's no OH or NH groups. Now the oxygen atom, which has a partial negative charge, that's used to stabilize the cation. So if you think of the example how we use a crown ether to solvate sodium fluoride, how it solvated the sodium ions but not the fluoride ions. This oxygen will also solvate the sodium ions. Now the sulfur bears a partial positive charge. This sulfur is not very accessible because of these 2 methyl groups, so it can't really effectively solvate the fluoride ions. Even though fluoride is attracted to the sulfur because of its partial positive charge, it's hard for it to get there because of the 2 methyl groups. Therefore, DMSO, dimethyl sulfoxide, is very good at solvating positively charged cations, thus allowing the negatively charged anion or nucleophile to be free to react with the substrate. So that's one way in which a polar aprotic solvent enhances the SN2 reaction. It's by freeing up the nucleophile, making it more reactive and more free to react with the substrate. So we can eliminate answer choice A. This is not a protic solvent, but an aprotic solvent. Now what about 12 crown 4 ether? We've already discussed the 15 crown 5 ether, but this is the 12 crown 4 ether. There's 12 atoms in total. You have 8 carbon atoms and 4 oxygen atoms. The 15 crown 5 ether was able to solvate the sodium ion. The 18 crown 6 ether is good at solvating a bigger ion, that is potassium, which is below sodium in the periodic table. And lithium is smaller than sodium. So 12 crown 4 is just the right size to solvate the lithium cation. As we can see, there's no OH or NH groups in this ether. So this too is an aprotic solvent. HMPA, hexamethyl phosphoramide, also known as hexamethyl phosphoric acid triamide. What you have here is a phosphorus atom double bonded to an oxygen with 3 nitrogen groups. And each nitrogen group has 2 methyl groups. So that's the name hexamethyl because we have 6 methyl groups in total. So that's HMPA. As you can see, nitrogen is not directly attached to hydrogen. There's no hydrogen bonds here. And so this is not going to be a protic solvent. This is an aprotic solvent. Now what about D, acetic acid? Acetic acid looks like this. It's a carboxylic acid, so you have a carbonyl group and a hydroxyl group. Because of the OH group, this solvent is going to be protic. Protic solvents favor SN1 reactions. Polar aprotic solvents favor SN2 reactions. So the correct answer for this problem is answer choice D. Now you need to be familiar with the other names. That's why I have more than 5 options here. Because when you see these solvent, you need to know if it's going to favor an SN1 or SN2 reaction. The other three solvents, they're all polar aprotic solvents. Acetonitrile, it's basically a methyl group attached to a nitrile functional group. A nitrile functional group is just a CN group with a triple bond between the carbon and the hydrogen. Between the carbon and the nitrogen. So this is acetonitrile. And this is the nitrile functional group. DMF, another polar aprotic solvent. This is NN dimethyl formamide. So you have an aldehyde functional group next to a nitrogen with two methyl groups. So that's DMF. It's also aprotic. There's no OH or NH bonds there. And then THF, tetrahydrofuran. It's basically a cyclic ether. You've seen this before if you have studied alkene reactions already, particularly with the hydroboration oxidation reaction. So like a crown ether, this doesn't have an OH or an NH bond, so that too is an aprotic solvent. Number 9. Which of the following solvents will work best for a SN1 reaction? Would you say it's A, tert-butanol, B, methanol, C, hexane, D, water, or E, ethanol? So we've seen that SN2 reactions, they favor polar aprotic solvents. SN1 reactions, they favor polar protic solvents. In both cases, both of these types of reaction mechanisms, they favor polar solvents, not nonpolar solvents. Hexane is a nonpolar solvent. There's no OH or NH groups. There's no special functional groups. A molecule that contains only carbon and hydrogen bonds, those molecules are nonpolar, and they don't work well for SN1 or SN2 reactions. So we can eliminate answer choice C. Everything else is polar because all of the remaining options have a hydroxyl group. So these are all polar. And because they have an OH group, they are all polar protic solvents, which favor an S1 reaction. So since all of them are polar protic solvents, how do we determine which one will work best for an S1 reaction? In this case, we need to look at polarity. As the polarity of the molecule increases, the reactivity for an SN1 reaction increases. Now, here's some data, according to my textbook, that really describes the relationship of polarity and the relative rate of an SN1 reaction. So if you have a solvent that is 100% ethanol, this solvent has been assigned a relative rate of reaction of 1. Now, if we had a mixture of 50% water and 50% ethanol, the relative rate of the reaction increases to 60. And if the solvent is completely composed of water, the relative rate of the reaction is 1200. So even though water and ethanol are both polar protic solvents, water is much more polar than ethanol. And the relative rate of reactivity is 1200 times greater than that for ethanol in an SN1 reaction. So the choice of solvent that you choose to use in an SN1 reaction matters. Using water over ethanol increases the rate of the reaction by a factor of 1200. So therefore, out of all of the remaining 4 polar protic solvents, water is the best. So D is the correct answer choice. Now let's rank the reactivity of these solvents, starting from the best to the last. So water, being the most polar, is going to work best for the S1 reaction. It's going to have the greatest relative rate of reaction. Now, which one is the second best? It's important to keep in mind that the OH group is a polar functional group, and the carbon-hydrogen bond is a nonpolar bond. So as the number of carbon-hydrogen bonds increases in the molecule, the less polar that molecule will be. Water doesn't have any CH bonds, so that makes it the most polar solvent out of those that's listed here. The second most polar one should be methanol, and then ethanol. Methanol has less carbon-hydrogen bonds than ethanol. So methanol, we can write it as MEOH. Ethanol, ETOH, this is CH3, CH2OH. So this has 3 CH bonds. This, we can count 5 CH bonds, plus a carbon-carbon bond in the middle, which is also nonpolar. So methanol will work better in an SN1 reaction than ethanol, because it's more polar than ethanol. Ethanol, we should expect to be more polar than terbutanol, since terbutanol has more CH bonds, and hexane will be the least polar. It's not even polar at all. It just has only CH bonds, so it should be the least reactive in an SN1 reaction. So that's how you can rank the Protic solvents in an SN1 reaction in terms of its reactivity. The key is to focus on polarity, is to ask yourself which molecule is more polar. That's going to be the one that's going to react better in an SN1 reaction. Number 10. What is the reagent that is needed to produce 2-methoxybutane from 2-chlorobutane? Well, let's write out the reaction. So here we have butane, and here we have a methoxy group on carbon 2. Actually, we need to start with 2-chlorobutane. And from that, we need to make 2-methoxybutane. So how can we do that? Well, let's look at answer choice A. For answer choice A, we have sodium methoxide. Answer choice B is potassium ethoxide. So we can eliminate answer choice B because this is OCH3. OCH2CH3 is not going to give us that product. But will answer choice A give us the product? We have a secondary alkyl halide, and we have a strong base. Methoxide is very close in strength to hydroxide, so both of these are strong bases. Whenever you have a secondary alkyl halide and a strong base, you're going to get an E2 reaction. This is going to abstract the proton, form a pi bond, and the leaving group is going to leave. So this happens all at the same time. Therefore, this is a concerted reaction mechanism, just like the SN2 reaction. So using sodium methoxide will give us an alkene. It will give us 2-butene as the major product. So we don't want to use that reagent. In order to get this product, we need either an SN1 reaction or an SN2 reaction. This is a substitution product. We don't want the E1 or E2 elimination product. Now, water is not going to help us. If we were to react 2-chlorobutane with water, instead of getting 2-methoxybutane, we'll get 2-butanol. So we can eliminate answer choice C. So we're between methanol and ethanol. So ethanol has too many carbon atoms, so that's not going to work. Therefore, the only possible answer is methanol. Methanol is going to behave both as the solvent and as a nucleophile in this reaction. And so this is going to be a solvolysis reaction, which is typically associated with an SN1 reaction. And here we have a secondary alkyl halide, a Protic solvent, that's going to favor the SN1 reaction mechanism. So let's go over the mechanism. The leaving group is going to leave. So that's the first thing. And then we're going to get a carbocation intermediate. And then the nucleophile is going to attack the carbocation, giving us this intermediate. And then we're going to use another methanol molecule to remove this proton. And so this will give us this final product. So answer choice D is the correct answer. Number 11. What is the major product of the following reaction? So we have this alkyl halide, and we're reacting it with potassium terbutoxide in tert-butanol. What's going to be the product of this reaction? Potassium terbutoxide is a strong base, and we have a secondary alkyl halide. The carbon that has the bromine atom is attached to two other carbon atoms. Now, whenever you have a secondary alkyl halide and a strong base reacting together, you're going to get an E2 reaction. So our final product should be an alkene. Now, we need to consider the type of strong base that we have. Terbutoxide is a strong, bulky base, and that's going to affect the major product that we're going to get. Because it's so bulky, it's going to selectively abstract a proton that is more accessible to it. Now, there are two protons on this carbon. Let's call it the green protons. And there's one proton here. Let's label this a blue proton. So we know that there's not going to be any rearrangements for an E2 reaction. So we can only get a double bond in this vicinity or here. Those are the only two possible products that we can get for this reaction. So we can eliminate answer choice A, and we can eliminate answer choice D. Now, even though we can get both of these products, our goal is to identify the major product. So which hydrogen is more accessible to this bulky base? Is it the blue hydrogen or is it the green hydrogen? It's going to be very difficult for terbutoxide to abstract the blue proton because of the methyl group. So due to steric factors, it's going to be hard for it to take the blue proton. Therefore, the green proton is more accessible. So it will preferentially abstract the green proton. We're going to get a double bond here, and the leaving group is going to leave. So this is going to give us this product, answer choice C. This is known as the Hofmann product. The other product is known as the Zaitsev product. When dealing with strong, bulky bases, they typically give you the Hofmann product. Strong, non-bulky or unhindered bases give you the Zaitsev product. The Zaitsev product is the more stable alkene, whereas the Hofmann product is the less stable alkene. So that's the answer for this problem. Answer choice C is the correct answer. Number 12. What is the major product of the following reaction? So everything is the same, but this time the reagents are different. We're not using potassium terbutoxide. We're using sodium hydroxide. Hydroxide is a strong base like terbutoxide. The only difference is it's not sterically hindered. Therefore, hydroxide can abstract both the blue hydrogen and the green hydrogen. The question is, which one does it prefer? So because hydroxide is a small but strong base, it can easily abstract that proton, even though the methyl is there. It's small enough that it can work its way to grab the blue proton. So the fact that it can abstract both the green and the blue proton, we need to look at other factors to determine which one is going to be the major product. By the way, we can't get A and we can't get D. The double bond, just like in the last problem, will form between the hydrogen and the bromine that leaves. So only B or C could be the answer. So we need to look at the stability of the alkene after the reaction. Now keep in mind, a tetra-substituted alkene, that's an alkene with 4 R groups, is more stable than a tri-substituted alkene, which has 3 groups. And that's more stable than a di-substituted alkene, and so forth. So to determine the relative stability of these two alkenes, we need to count the number of R groups that are attached to the double bonded carbon atoms. So these are the double bonded carbon atoms, and those two double bonded carbon atoms are attached to a total of 4 other carbon atoms. So this would be a tri-substituted alkene. And here are the two double bonded carbon atoms here, and they're attached to two of the carbon atoms. So this is a disubstituted alkene. Trisubstituted alkenes are more stable than disubstituted alkenes. Therefore, hydroxide will preferentially abstract the blue hydrogen to form a more stable product. And this more stable product is known as the Zaitsev product. The other one, as we mentioned before, the Hoffman product, contains the less stable alkene. So that's going to be the answer for number 12. Answer choice B is the correct answer. 13. What is the major elimination product of the following reaction? So everything else is the same, but this time we're not using a strong base like sodium hydroxide or potassium terbutoxide. Instead, we're using methanol, which can behave as a weak base or as a nucleophile, depending on what reaction mechanism is occurring. So what's going to be the predominant mechanism here? Well, we have a secondary alkyl halide just like before, but this time we have a protic solvent. And so those conditions favor the SN1 E1 reaction. These two reactions tend to occur together. So whenever you get the SN1 product, you can get the E1 product. But there are things that you can do that you can increase the yield of the E1 reaction over the SN1 reaction. And one of those things is by heating the reaction mixture. When you raise the temperature, the E1 product, you're going to increase the yield of the E1 product over the SN1 product. So that's usually when the E1 product will dominate, is if you add heat to the mixture. It favors elimination over substitution. And looking at the question, we don't want the substitution product. We want the elimination product. Therefore, we're focused on the E1 reaction. Even though we could get the SN1 product for this reaction, that's not what the question is asking for. We want the elimination product. So, which of these answer choices will be the dominant E1 product for this reaction? So since we have elimination reaction, methanol is not going to behave as a nucleophile. It's going to behave as a base. So let's go over the mechanism. The first thing that will happen in an E1 reaction is that the leaving group is going to leave. And we're going to get a secondary carbocation intermediate. Now, whenever you have a carbocation, you want to find out if that carbocation will rearrange. It's going to rearrange if it can form a more stable carbocation. Notice that this secondary carbocation is adjacent to this tertiary carbon. And so what's going to happen is we're going to get something known as a hydride shift. This hydrogen is going to move towards the carbocation. As that hydrogen leaves the tertiary carbon, the plus charge is going to move to that tertiary carbon. And so we're going to get a tertiary carbocation intermediate. Now, once we form that tertiary carbocation intermediate, it's not going to rearrange anymore because it can't form anything more stable than what it is right now. So at this point, the base is going to come in and abstract a proton. Now, it's going to abstract a proton that is one carbon away from the carbocation's center. So it can abstract this white proton. Let me redraw this so we can color code all the different protons that it can abstract. So here's the plus charge. It can take, let's call this the blue proton. It can also abstract a proton from the methyl group. We'll call it the green proton. And it can also abstract that proton as well. So each of those protons are one carbon away from the carbocation center. The question is, which proton will be abstracted? So it all depends on the stability of the product. We could form a double bond here, here, or here. So we could get this product. We can get this one if we abstract the blue proton. If we take the green proton, we can get that one. We can't get C because the carbocation is too far away to get this particular alkene. So we can eliminate answer choice C. So now we need to determine which of the remaining 3 alkenes is most stable, because that's going to be the major E1 product. It's going to be the most stable alkene that this reaction can form. So let's begin by identifying the double bonded carbon atoms. And let's count how many R groups they're attached to. So for answer choice A, there's only 2 carbons attached to this to the double bond. So this is a di-substituted alkene. Now looking at answer choice B, there are 3 R groups, or 3 carbons attached to that double bond system. So this is going to be a tri-substituted alkene. And for D, for answer choice D, we have 4 R groups on the double bond. So that's a di-substituted, not a di-substituted, but a tetra-substituted alkene. So this is the most stable alkene that we can form. Therefore, answer choice D is going to be the answer. So let's finish the mechanism. Methanol is going to act as a base, and it's going to go for the red hydrogen. The carbon-hydrogen bond will break. Those electrons will be used to form the pi bond here, giving us this particular product. So that's going to be the answer for this problem. Answer choice D is the correct answer. Number 14. Which of the following steps will not occur in the acid-catalyzed E1 alcohol dehydration reaction shown below? So in order to get the answer, we need to be thoroughly familiar with the mechanism of that reaction. So let's go ahead and work on that reaction, and then we'll identify which steps are correct. So once you mix water and sulfuric acid, these two will react. Sulfuric acid is a strong acid, and it's going to transfer a proton to water. As it does so, it's going to become bisulfate and H3O+. The Ka value for the first proton of sulfuric acid is significantly high. The second proton doesn't come off as easily, but the first proton, it easily comes off sulfuric acid. So we're going to have a lot of H3O+ and HSO4- in the solution. Now H3O+ is a stronger acid than HSO4-. So it stands to reason that the first step will be the protonation of cyclohexanol by H3O+. So that's going to be the first step in the mechanism. So A is okay, which means we're looking for the step that will not occur. So we can eliminate A because this step will occur. Now what's going to happen after protonation? Let me redraw that better. So after this step occurs, what's going to be the next step? Now this is an E1 reaction, which means we need to form a carbocation. So the leaving group, water, has to leave. Water is a better leaving group than OH. The hydroxyl group is a bad leaving group, but once you protonate it, it becomes a better leaving group. So this step is okay. This is going to generate the carbocation. Now let's look at answer choice B and D. Our goal is to get an E1 reaction. B is not going to happen because water is acting as a nucleophile. If water behaves as a nucleophile, reacting with the carbocation, it can turn back into cyclohexanol, which is what we don't want. Rather, we want to remove water. We want to dehydrate. We want to dehydrate cyclohexanol by removing water, forming an alkene. In this case, the only way we're going to get that is if water acts as a weak base. And that's what it's going to do in answer choice D. Water is going to abstract the proton that we see here, forming an alkene, which is the product of an E1 reaction. So steps A, C, and D occur in this actual mechanism. However, answer choice B is not a step in the E1 alcohol dehydration reaction that we have below here. So this is the correct answer. This step does not exist in an E1 reaction. This is more like an SN1 reaction, where the nucleophile attacks the carbocation. Number 15. List the following carbocations in decreasing order of stability. That is, we want to rank them from most stable to least stable. Well, let's begin by identifying what type of carbocations that we have in the first place. So this here is a tertiary carbocation. The carbon with the plus charge is attached to 3 other carbon atoms. Here we have a secondary carbocation. This one is tertiary, but it's allylic, since the plus charge is 1 carbon away from the double bond. And this is a primary carbocation. Now, what you need to know is that tertiary allylic carbocations are more stable than just regular tertiary carbocations. And the reason for this is that the carbocation is stabilized by resonance. We could take this double bond and move it here. And so this will give us a resonance structure that looks like this. So the positive charge is shared between 2 carbon atoms as opposed to just being stuck on one. So what you need to realize is that a tertiary allylic carbocation is more stable than a tertiary carbocation, which is more stable than a secondary carbocation, which is more stable than a primary carbocation. The reason why tertiary carbocations are more stable than primary ones is because as you increase the number of carbon atoms on the carbocation, those carbon atoms, they can donate electron density to that carbocation, thus stabilizing that positive charge. Methyl groups are weak electron donating groups. They can donate electron density through the sigma bond, which is known as the inductive effect, or they can also donate density by means of the overlap of atomic orbitals, that is by hyperconjugation. So here is basically an empty p orbital with the positive charge, and some of the electron density from the CH bond, some of that can overlap into this empty p orbital, thus satisfying that positive charge desire to be neutral. So that's how a tertiary carbon or a tertiary carbocation is more stabilized than a primary carbocation, is because of the extra CH bonds that are next to it can help stabilize that positive charge by means of the inductive effect and by means of hyperconjugation. Now let's go ahead and finish this problem. So we know the tertiary allylic carbocation is going to be the most stable. So that's number 3. Next we have the tertiary carbocation, which is compound number 1. That's more stable than the secondary carbocation, compound 2, and the last one is compound 4, the least stable. So this corresponds to answer choice C.